Hello guys, welcome back. So today we're going to be talking about spectroscopic and other tools that you would mainly use in the field of analytical chemistry. Um, so we have, we really have three stooges. I'll introduce you to the what I call the three stooges here: the mass spectrometer, the proton NMR machine, and the IR spectrometer. So let's first start off with mass spectrometry. So mass spectrometry is a tool used to measure the atomic mass or the mass of a sample. Um, the way it works is sort of beyond the scope of the syllabus. However, I think it's important to I think it'll be important to explain briefly how it works in order so that you can understand sort of how it works. So if we switch over to the other screen, let's sort of draw a mass spectrometer. So if we have that, and then so the way a mass spectrometer works is that you have a magnetic field here. So B, we use the symbol B in physics to denote a magnetic field. So we have a very strong magnetic field, and the way it works is that um, if you have any charged particle, so be it positive or negative, that magnetic field will exert a force on the charged particle, and as a result of that, it'll push it towards this curve here, and we can actually measure the mass of that based on like the deflection, how much it deflects, how much the force deflects the charged particle's trajectory. So here, let's say I had a proton come in here. Um, what'll happen is that the force will exert this B field will exert a downward force, and you get the proton being displaced here going down the curve, and now its trajectory is changed. Um, if we were to put, I think for those that take physics, this might be helpful. So basically, what we amount to is that uh, if we what we can do here is that this is actually a centripetal force, and as a result, we can um, sort of manipulate the fact that it's a centripetal force, and we can write that QVB equals mv squared over r. And when we change the trajectory, it's this radius that we actually are measuring. And we can rearrange for m. We can rearrange for m so that such that m equals r q b over v. So we can rearrange that. So because we know the velocity of the particle, we know the velocity of the particle, since that's like we know the speed that we ejected the particle at, since we ejected it. We know we can measure the radius experimentally. We know the charge of the ion. Typically, it would be +1. And we know the strength of a magnetic field. Again, that's a constant that we can just take off the ring here. Now, this only works with charged particles, so in order to do that, most things have to be ionized. So we have to remove an electron from it, and then, okay, we can deflect it in the magnetic field. And we can use it for two things. The more simple use, can I switch back here to my other display? Yep. The more simple uses, we can actually use it to take the relative abundance of each isotope of an element. So here, this is the mass spectrum for elemental carbon. It measures it in terms of detector response. We can't directly measure the mass, but we can calculate it. But what the detector does detect is it'll hit certain spots, and if one isotope is hitting a particular spot more, the detector response is higher, and then also too, the detector response is higher at that spot. So then, as a result, you'll get a higher peak there. So for example, for elemental carbon, there's a small little itty bitty peak here at 13, and then there's a much higher peak at 12. And this corresponds to an abundance of 98.89%, and 1.11%. And then we can also, what we can do from this data is we can take a weighted average. So we can do the percent times the mass of that peak plus the percent times the mass of the other peak, and so on and so forth, to take an average. So it would be the sum of, yeah, that's how we would take the average. We take the percent divided by 100 and then multiply it by the mass that we record. And at that peak, take the sum of each of that. So here, if I write that sort of mathematically, what we can do here is, so back, let me erase just everything. So select all, delete. So from the experimental data, we can know that RAM equals sum of Mi times so from I equals 1 to n, whatever. So that's the formula for the relative atomic mass if you're given this sort of data. Now, there's another use for this data, and when we go here to, I need to find it here in my notes. Hang on. Yeah, we can also, now, that's a pretty simple view of it. Now that I found the correct section in my other set of notes, we can also use it when we analyze organic compounds, and the way we can do it for organic compounds is a little bit more interesting. It switched back? Yeah, okay, it switched back. Okay. Excuse me. Another way we can, now, that's all very well and good. We can take the relative atomic mass. However, what I think is more interesting is that when we say we had the mass of say we had an organic compound and we don't know what it is. One way we can use mass spectrometry to help us is that we can ionize it and we can find the molecular mass of the compound. And modern computers are so good, they can actually get such a precise measurement that we can actually calculate the molecular formula just by having that mass spectrometry data, because it's nowadays so accurate that since we know the mass of the individual atoms to such a high degree of accuracy, the computer can actually calculate, okay, what sum of atomic masses will yield this particular mass, because we have such accurate data. So we can use it to get the exact molecular formula and molecular mass of the compound. So there we go. That's two pretty important things right there. Another thing, however, we can measure, and I think what might actually be probably most useful to you, is that when molecules become ionized, they generally tend to become unstable and they fall apart. And we can actually, these fragments, these molecular fragments of the molecule can, hit the detector, or alternatively, we can notice gaps in the detector. We can notice gaps, differences in mass that correspond to a particular group, to a particular functional group, or a particular branch type. So, and this is what we refer to as a fragmentation pattern. And a fragment may be evident if the mass associated with a certain peak was 1 plus, or there's a difference there, in which case the fragment was neutral and the remnant of one molecule was charged. So what we can generally see is that, so here's some common fragments that you'll encounter. So if you get a mass difference of 15, or you get a peak at 15, it corresponds to a methyl group. For 17, if you get a difference of 17 or a peak of 17, it's an OH group. You're more likely to come across this in terms of a difference. For 29, you can either have two options, this ethyl group here, or this this aldehyde group. Now, how do you make that determination on what it is? Well, you would use other spectroscopic data, which we'll get into later. And then lastly, for a fragment of 45, it would be typically a carboxylic acid. So that's sort of that's sort of what we could use mass spectrometry for. We can either use it to take the isotopic masses, and then more specifically, we can use it to take the molecular mass of a certain compound that we don't know, and from that we can get the molecular formula, and then we can also get these fragments can tell us, okay, what parts of this molecule is it made up of. So if we had a fragment at 15, we know there had to be a methyl group in that molecule. So that's mass spectrometry, and I think it's one of those more important things that you'll probably yeah, that's mass spectrometry. The next tool in our toolkit would be IR spectrometry, IR spectroscopy. So the way it works is that atoms and molecules, their bonds are typically vibrating with a certain frequency, and if we shine a certain frequency of infrared light, we can actually cause those bonds to vibrate a little bit faster, or they can vibrate with more energy, which we can actually measure in the lab. And for those again that take physics, that would be corresponding to constructive interference within the wave. If you imagine a bond is a spring, like that obeys Hooke's law, we can get an effect called well, for those that are interested in engineering, it would be called resonance. But basically, we can amplify that signal, that we can amplify that vibration, right? And when we do that, it corresponds to a certain frequency of light, and we can correspond that to a wavelength, which we can correspond to a wave number, since wave number is the inverse of wavelength. And basically, all right, a bit of a technical explanation there, right? So that's sort of the technical explanation behind it. Now, what do you actually need to know how to do? It's pretty simple. This is a sort of transmittance. It's a graph of transmittance versus wave number, and if there was no sample there, the light would just pass through there. It'd be 100% transmittance at all wavelengths and frequencies, and so on and so forth. However, because of the fact that certain compounds will absorb certain wavelengths and cause them to vibrate more, you will get these dips. You will get these dips here that correspond to these certain wavelengths, right? So here we have a dip here, which looks to be about 3350. It looks to be about 3350, and then here we have a peak at 3000, and so on. And then here we have from 1500 down, we have what we call the fingerprint region, which basically, if you have an idea as to what the compound is, it's like a fingerprint. You can look it up in a book. I'm sure there's a big book or on a table or whatever of all the known compounds, and if the fingerprint matches, then congratulations, you have the compound. However, from 1500 onward is called the functional group band, and this is the band that you probably care about. And according to this chart here, a peak at 3350 would correspond to here we have a band 32 to 3600 that is strong and broad, so it would probably be an alcohol, and it turns out this is butan-2-ol, and that's right. And then correspondingly here, there's bands at about 3000. Bands at about 3000 correspond to CH bonds, which, believe it or not, there's a ton of them. So there's that. So that's really all there is really to it. That's really all there is to IR spectroscopy. So it's not, while the explanation I may have given may have been complicated, in reality all you need to know how to do is, okay, find where the dips are, and then use this chart here, which is given to you on your exam, to identify what those dips are. Lastly, we have this one is pretty hard to understand conceptually, and I think a proper explanation is really warranted. So, but before we get into that proper explanation, we need to talk about hydrogen environments. And if you don't know, if you couldn't guess, the last bit here is nuclear magnetic resonance, or proton NMR spectroscopy. So what a hydrogen environment is that it's hydrogens that have the same sort of bonding to it, I guess. It's hard to describe, and you are expected to know how to find them. So sort of what a hydrogen environment describes is how many hydrogens are in a particular chemical environment, and by chemical environment I mean what's the hydrogen bonded to, and then what's that bonded to, and so on and so forth. So I think it's worth actually taking a look at an example here. So, and then we have to get the ratio of the environment. So, uh, yeah, it's hard to define, you know, what exactly a hydrogen environment is. However, you can more or less think of it as like, okay, what's a hydrogen, what's it bonded to, and then what's that bonded to, and what's that bonded to, and so on and so forth. So, for example, here with here, let's draw random molecule. Let's say we had ethanol. So another way you can think of hydrogen environments is, okay, take the vantage point of this hydrogen here, and then what do you see? And then what do you see from that vantage point? And then here you would get the same vantage point, likewise here, but here you would get a different vantage point because you would be seeing these three and then that. Whereas if you go from here, you're only really seeing that, and then if you go from here, you're only seeing that. If you only go from here, you're seeing that. That's another way people tend to do it. The way I do it is, okay, what I say is, okay, this H is bonded to this C, which is bonded to this C, which is bonded to this O, and this H is also bonded to a carbon, which is bonded to a carbon, which is also bonded to an oxygen. And then same here, carbon, carbon, oxygen. Whereas if you were to take this hydrogen, okay, it's bonded to a carbon, which is bonded to an oxygen. I sort of pick one end of the molecule. So let's say I pick this one, the one that I'm marking, and I trace my path to go here. And if I follow the same sort of path to go to the other end of the molecule, it's in the same environment. So we would group these three together, these two together, and then these together. And there's three hydrogens in this environment, so 3, 2, I should probably do a better job circling that, and then 1. So that's sort of a brief explanation as to how hydrogen environments work. It's more or less what is your vantage point from that particular hydrogen? What does the rest of the molecule look like, I suppose? It's a bit of a tough concept to explain. Hopefully that sort of made sense as to what I was doing there. I'll probably do some more videos going over this stuff. But now that we know what that hydrogen environment is, we can actually get into proton NMR spectroscopy. Basically, the hydrogen atom is unique in that if you subject it to a magnetic field, the nucleus has spin states like electrons do as well. And if you subject it to a magnetic field, there is a difference in energy between those two nuclear spin states. And if you shine the right type of light on it, if you shine the right frequency of light on it, you will cause it to go from one spin state to the lower spin state to the higher spin state. So, and that difference in energy corresponds to radio wave frequencies in the radio wave spectrum of the electromagnetic spectrum. And more than that, if you bond it to a different different chemical environments can affect that difference in energy between the two energy levels. So if you are bonding to an oxygen here, you might have, so generally the trend is that if there's more electronegative elements bonded to it, the difference in energy between the nuclear spin states is higher. So we can leverage that fact to sort of, determine hydrogen environments because they would absorb different energies. So the hydrogens in this environment, in this environment would absorb a slightly different energy than the hydrogens in this environment, which would absorb a different energy than this hydrogen here. So that's sort of where hydrogen environments come into play. They are regions of space, they are regions of hydrogens that absorb the same frequency of light. I think that's a good way to describe it. Now, how do you trace that on a molecule? You just do what I did 2 minutes ago. So now that's what that corresponds to, and then the peaks correspond to, and then the integral, the area under the curve, corresponds to the number of hydrogens in that environment. So if I go back here to my notes, which I was, so we can take the chemical shift of the peak to determine sort of what hydrogen environment it is, and then we can take the integration to determine how many hydrogens are in that environment. So here, if we consider ethanol, this hydrogen here corresponds to a peak of about 4.5. This one here corresponds to a peak of about what is that, 3.5, and then this one here corresponds to a peak of 1.1. So 4.6, 3.6, 1.1, and then it's in a 1 to 2 to 3 ratio, and there are 3 peaks since there are 3 sort of peaks there. And this is technically considered a low resolution NMR, low resolution proton NMR spectroscopy. There's also high resolution, which is for the higher levels, not for the standard levels, but that's sort of that there. And then here's sort of a table of hydrogen environments that you could be expected to run into. This is given in your data booklet, so I wouldn't memorize these, but when you pick a hydrogen environment, you see here, oh look, there's 1 to 6, and then this is also goes from 4 to 6. So what if you get a peak at 4.5, and how do you determine which one it is? You would use the integration trace, which they would either have to give you, or you would sort of have to guesstimate with your eyes. You'd have to say, okay, this area looks to be about 3 times as big as that area. You would have to use sort of clues like that to to help you pick one. And then 2, you would also have to use other spectroscopic evidence, such as mass spec or IR spec or combustion analysis, and so on and so forth. I'll probably do a whole separate video, or a couple of videos even, sort of explaining how you use these analytical techniques to determine what a compound is. But that's sort of how it works, and sort of what you need to know off the IB syllabus. So with that, thank you for watching. I apologize for the extremely long video length. Don't forget to like and subscribe.